Good evening, everyone. On behalf of Pre-Science in Silico, I welcome you to the Fusion Talk. A few words about Pre-Science in Silico. At Pre-Science in Silico, we team up with both industry and academia to tackle challenges in drug discovery and material science. The idea for this talk series came from our wish to create a space where experts from different fields can share their valuable insights. We are proud to be the first Indian company to create our own drug discovery software with advanced AI features. Pre-Science was founded by academicians who wanted to make AI-powered discoveries in drugs and materials accessible to everyone, aiming to redefine the landscape of scientific innovation. The title of today's Fusion Talk is Supervised Machine Learning Models for Predicting Chemical Properties. Let me introduce the speaker for today's talk. Professor Natalia Cordeiro is an Associate Professor of Chemistry at the Faculty of Sciences, University of Porto, Portugal, and now heads the Chemistry Materials Modeling Research Group at the Associated Laboratory for Green Chemistry. Initially working on molecular simulations of ionic solutions and fluid interfaces, driven by challenges in electrochemistry, her current research primarily revolves around leveraging machine learning tools. This involves predicting property, reactivity, and assessing the safety of chemicals and nanomaterials, with direct applications in the field of drug and materials design. She is an author of more than 350 scientific publications, 25 book chapters, and 150 oral communications at national and international conferences. A note to the attendees, please feel free to feed in your questions in the chat box, and we'll attend to those questions at the end of the talk. With that, we are very excited to welcome Professor Natalia to our head office today for an in-person talk, a very special occasion for all of us at Pre-Science. I'm sure you will enjoy this talk at the interface of chemistry, machine learning. With that, I would request Professor Natalia to share her screen and start the talk. Thank you.
Hello, everyone. Well, thank you for your kind introduction, and I will talk about supervised machine learning models for predicting chemical properties. First of all, why we are trying to develop in our groups kind of inverse design, really, and we are. As a proof of concept, we will start with the property prediction, unleashing the power of data, and I will tell you about two types of property predictions that we have done recently. Basically, one of them is already shown there, the catalytic epoxidation of small alkenes and alkenes in vanadium-catalyzed. And well, and you can also see we have already published similar work about predicting the free energy of solvation of molecules of chemical recently, using the same strategy that I will show you today. So, what's the feature really about machine learning? Computational models to solutions to chemical problems using data science, machine learning. Those are data driven. When you use the chemical data to set up the machine learning models, those should be explanatory, which is a kind of approach, and that kind of in a form of a tailor-made approach. And for instance, in this case, in the case of epoxidation of small alcohols and alkenes, we have this is the kind of reaction we are tackling. And we have several industrial intermediates, ethylene oxide, tricidol, propylene oxide. And by the way, this catalytic epoxidation of small alcohols and alkenes, they are produced around 22 million tons per year, and they are used in several commodities like pesticides, plastics, flavorants, and fine drugs. So find the best catalyst for this type of reactions, it's really important, and it gives up 20 billion per year probably the industry. And we have, if you have an active catalyst, you can have, if you have a better catalyst, you can have a faster reaction with the products. And so there are several, the vanadium catalysts are often used, and there are several scaffolds, and we want to find which one is the best one for catalyzing this reaction. And in fact, there is a lot of unexplored chemical information and about this type of reactions. Well, we can also see our review that we published recently also about sustainable epoxidation of small alkenes and alcohols. And the question is, can we use data? How? First, machine learning is a low-cost methodology and adds value to industry, to data. And why? Because it can optimize chemical process in industrial applications and predicting chemical features and process safety also. But nevertheless, it's difficult to develop algorithms for specific and complex problems like that, like finding a catalyst for a reaction or predicting another type of chemical property, which I will talk about also, like the enthalpy of vaporisation of molecules. Because why? Because predicting it with petrochemical calculations or simulation ones, it's a high computational cost and a narrow chemical application. It seldom gives correct predictions. So this is the problem that we have. For instance, for predicting the enthalpy of vaporization of molecules, you have the best model is from Karagensi, if I'm spelling it correctly, that it gave an error of prediction of 10.6%. So our main aim here was to decrease a lot this type of error. And so our goal was to develop machine learning based models that will predict chemical properties with unprecedented speed, fast, and also accuracy based on existing experimental data sets. Or in case you don't have enough data, you can also calculate the data. So what we did was a database creation. We use Skyline and the RD kits for chemical description, for describing the molecules. And then we build the machine learning model, and we try to be most predictable as possible. And so we have then the property prediction, and we can make complex experiments in seconds without going to the lab. So to be honest, we tackle the disadvantage of machine learning black box design to be fast and also accurate. And in this case, as I will show you, we had some, we start by collecting the database, and we use the chemical descriptors of RT-Kit, which are several descriptors and are well known. electronic abstraction and for instance, ESA is the following surface area and other ones. And we build the model, and then we can use the same type of thing for other type of machine learning models, which are supervised algorithms. For instance, for the case of the catalysts. So this is the workflow that we use and how we address prediction and explanation. This will be more in detail here. For instance, for the enthalpy of vaporization, we use the SMILE strings, and we have input from the literature and online experimental databases. So with the SMILE strings, we using RTKit, we compute the chemical descriptors for all the molecules. We had around 1,300 different molecules. And this is how we convert chemical data into descriptors. And there are several softwares that can within a specific molecular database, you can specifically build the SMILE string, and then using the RTKit software to compute the chemical descriptors. And then how do we construct the model? So the database was, we had more, I'm sorry, I said it was 1,300, but then we increased the number of molecules, I'm sorry. So we had around 2,000 molecules and over 15 different functional groups. So we have a kind of very heterogeneous database. And we use 106 chemical descriptors from the RTKit. And what we usually do, we start by the mol file. We use OpenBabel, which is a well-known software, and we convert to the SMILEs. And then with the RTKit, we use the descriptors. Here it's also important to probably to train a machine learning algorithm, you normally have to split the database into a training and a test database. And what we do here is we try to see the loading of the train database. So before we go to the hyperparameter tuning, what we do is, without hyperparameter tuning, we do the several models, and we change the ratio between the number of molecules that we put on the train and the test set to see which is the best train load that we should use for our models. And then the next step is to do the hyperparameter tuning. And of course, we also have to test our models then with an external database. And in this case, what we did was we tried to model the enthalpy of vaporization, basically because it's an important problem for the volatile organic compounds, which are pollutants. And so what we use this model without so our external database in the molecules that we connected, we didn't put any box, and on our external database were only box. So we could then make a model that could be useful for reducing the box, which is important also. And so after we decide which is the loading of the training and the test set, we use, usually are the methods that we use. We use random forest, gradient boosting, spot pattern machines, and multi-layer perceptron or deep neural network if it is. But basically, multi-layer perceptron is the same as a deep neural network with less hidden layers really. So in this case we only train the multi-layer perceptron, and then we do a kind of hyperparameter using cross-validation, hyperparameter tuning. And so we developed the 4 machine learning algorithms, and we using the regressive. Well, we could use, sometimes we use classification, but in this case it was more, we had continuous data because the enthalpy of vaporization is continuous, so we use regressive aggregation. And then, well, this is the training loading, although here it's not, we didn't include the multi-layer perceptron, I'm sorry, because we included it later on. And that's how we secure that we have low prediction errors by choosing the best training and the test set. And then we use the training only for developing the models. And we had around, as you can see here, we had around, oops, where is the pointer?
It's in the
it's here, no?
Yeah.
Yes, we have over 15 different types of molecular structures, so it really ensures heterogeneity and model representativity also. And so then we do the usual thing by doing the hyperparameter tuning of the models, and what we get is we got the score test for the gradient boost already reasonable, using the training set, and for the random forest, these were the best ones, I believe, in relation to the other ones, in relation to the support of better machine and the multi-layer presented. But our target was to go even having an error of lower, really. I mean, percentage error lower. So how can we do this? The next step we do is usually after having the best models, what we do is we do a factor optimization. And in that case, we can use, well, here now, we only use, what we used was basically permutation importance, but we can use other types of optimization algorithms, which are not quite common, like, I don't know if you're, well, probably the computer science know for sure, which is the hands algorithms. You know, we also use ant algorithms sometimes. We have used also the gray wolves also. Gray wolves, another type of or Monte Carlo optimization also. But in this case, what we did was, this paper should be soon published also. And what we did was permutation importance to try to see which were the ones that we identified 3 types of key descriptors. This is volume, surface area, electronic and structure. Well, you have here the numbers, some are structural, you have the number of heavy atom counts, this is also structural, and well, and you have also some which are more like this one, which are more electronic, and also the VSA, the volume surface area. And we select the best ones to yield the optimized calculations by subdividing the values of the enthalpy of vaporization and trying to see how they distribute really. And so we aim for also to get an explanation of the factor importance. And what we don't know why it goes always slow here. And so we realized that increasing by the presentation importance, we realized that increasing the column surface area led to a higher prediction error. And also in the other case, which I don't know why, the increasing complexity led to a lower prediction error. And so we optimized instead of using the 106 descriptors, we kind of optimized by doing this really. And you can see the difference between all the 106 descriptors and the optimized one. So you can see that we could, with the optimized ones, instead of using the 160, we can use, sometimes we also use, and we also try to see if they are correlated or not, reduce and things like that. And we end up using 67, we end up with a much lower in absolute error in this case, which is well below the 4 kilojoule usually barrier for the chemistries really. So, and we end up also explaining by seeing the optimized descriptors, so how a model was able to grasp the chemical meaning. So we could see that molecules with a smaller surface area of low electronic and topological environment resulting in a small van der Waals force seem to provide better predictions. And so this was our aim, to decrease the error, and apart from that we can explain what we have really. Sometimes apart from the factor importance, you can also use the sharp values, to try to explain better. Well, and we are also, so this is a comparison with other, I didn't put this is a comparison with only the 3 algorithms. I still do not have this with the multilayer. We did also with the multilayer preceptor, but didn't put it on the graph, I'm sorry. But you can see that the best one is looks like the gradient boosting. Yes.
Yeah, gradient boosting, yes.
And apart from that, comparing with all the predictions that that have been done in the literature for predicting the standard vaporization enthalpy, it was much lower than the other ones. So we had really, and also the model was reliable across the different heterogeneous groups that we had. So we successfully built and optimized the machine learning prediction model, and we also could explain its predictions also. And now we are doing also the same type of thing, the same type of scheme with this is an important part. We also did the external validation with the platinum organic compounds, and which was also pretty good. So these were molecules not seen at all, so it was pretty good. So our model was externally validated by a benchmark database. And this is a comparison with other predictions. So you can see that part of these predictions are based on quantum chemical calculations, which are expensive also, and some are based on type of contribution, group contribution methods and things like that. But our model was predicted the standard vaporization enthalpies of an external database with a better percentage error than previous benchmark attempts. So we're quite satisfied with this model. And we are doing the same type of scheme basically for now for the catalyst for predicting. In that case, we are going to use also another step, because we need to have a lower activation energy for optimizing the catalyst, and also a yield also. So we have two types of properties, and what we try to do in such a case, or what we are going to do in such a case, is to use a kind of multi-objective optimization. You know what that is, the multi-object optimization. So we do the machine learning model for each type of property that we want to predict, and then we use, well, we could use several types of models, but in our case, that was what I told in Campo. You listen. In our group, normally we use the zerability approach. You know that? Oh, I can tell you another time about it. So in this case, our models were fast and explainable, and hopefully they can be replicable and for thermochemical predictions. And also explainable, which is important. And now what we are going to do is to try to use same type of scheme for predicting another type of properties, like for developing the best catalyst for the epoxidation reactions. And in case that, in this case, it's the L prediction, but also there are two properties that we could optimize really. This is still undergoing this model, but basically we also reduced in this case we reduced the fixtures that we are using here. It was not only the RT-kit scripters, we use the experimental ones, like things like that have been done, type of number of hours, well, several experimental scripters that we knew from the data, from collecting the data. And so what we also did the best training test load, and we did that. Then we did also use the same type of machine learning algorithms to do hyperparameter optimization, and we also trimmed down the scripters for getting an optimal prediction. And in this case, I believe it was also, although this is still ongoing work. And what we intend to do is this, which is to achieve, is to try to design new catalysts based on literature data, going the other way around. If you know the descriptors, you can go to either and do an inverse design. That's what we are trying now to do. Well, in this case, we had also the descriptors that you use. We could, for instance, describe the catalyst and the ligands, and well, it was also an explainable model. And so we could say which was the best chemical features to have for the catalyst and also for the ligands also. We should have, for instance, for the ligands, decreasing branching and low cycling nature, and decrease the electronic state on the surface area. And so these are the machine learning model provided the best features to guide the catalyst design, which is, as I told you, the next step that we intend to do. And in this case, thank you for your attention. If you want, I can also show you the other type of scheme because it's a bit different than which is normal use. The
Other, yeah, sure. Means we still have another at least 10 minutes.
Also,
so I can.
Can you? Yeah. Well, the scheme that I'm going to show you, it can be used for also for property predictions or whatever, but it can be, in this case, I believe it was used to assessment of toxicity of nanoparticles, really. But it's a thing that you probably do not know, and we have also and it's a classification method in this case, and we have also a GitHub repository with the software, the one I told you, PsychoX. So in this case, it was to assess the toxicity of metal oxide nanomaterials. This speech is
Already shared?
no.
Extra one. Share. Now you can see it. Now.
This is a bit different because it's a perturbation theory machine learning approach. I don't know if you ever heard about it or not. Why this? Well, in this case, it was for assessing the toxicity of metal oxide nanomaterials, but it could be for any other type of property, really, or in drug design or whatever. Well, this is only why we should nanotechnology, you know, that is rapidly expanding, and the problem here is that there is a large number of products containing nanomaterials, and the problem is that they offer technical and commercial opportunities, but they pose risks really to the environment and raise health and safety concerns for humans and for the animal. And well, this was let me see if India is here. I don't know.
Asia and Oceania is here, so we can look at the Asia data. So it's 52%, 52.3%. Yeah.
Yes, you have Asia and Russia. So this data is from two. Perhaps it has increased slightly. Well, and there is India there. Also, you can see also
the red plot. Yes.
The green one is China. Well, and so we need to have measures to fast and well address the environment threat and potential toxicity of nanomaterials and nanoparticles because basically because covering filtering with this type of techniques, high throughput screening and light content analysis, and although they are playing a key role for the efficient assessment of the toxicity, they have high costs, times, and so we need to have in silico models and to, as you can see, with these models, we are predicting not only the toxicity really, but the ecotoxicity, the cytotoxicity, and the genotoxicity altogether. These models are quite powerful in that respect. And also so what we use is we integrate in silico models for the analysis, for instance, of nanomaterials hazard and risk, but for several types of toxicities and ecotoxicities, and to have a final sustainable nanomaterials. How do you do? Well, classical models that are used are based on the fact that the toxicity of the nanoparticles correlates with the properties encoded in particular structural factors with shorter descriptors, and usually one tries to derive a model that relates slowly one desired endpoint with the nanoparticles and descriptors. But first, those classical models do not attempt to predict the toxicity again. Well, first they do not attempt to predict the toxicities against, or they do attempt to predict the toxicity only against one biological target, and do not take into account the role of other factors like the experimental conditions follows and so forth. So they have disadvantage. What we try to do with this model is to set up a unified model which can be used for several types of toxicities, several types of species, and under diverse experimental conditions. How do we do this? Basically, this is only how can we overcome the limitations of ignoring that the endpoint response values depend on the type of experimental procedures or theoretical calculations employed? That's true. If you do a model with data coming even from theoretical calculations, you can have different results if you use I don't know, in the case of a periodic DFT, if you use PBA or if you use another type of density functional model, no? So this is, that's why in our group and in another group in space especially, we apply the perturbation theory machine learning model, which is based on the box-Jenkins moving average approach. And what do we do? The box-Jenkins approach is an approach used in time series analysis, but what we use here, we don't expect, we use it for basically to modify the original descriptors according to the experimental, under the experimental conditions used. So we modify, we have the initial descriptors can be whatever you want, experimentals or chemical descriptors of the structure, whatever. And then we have, we subtract from the original descriptors, we subtract an average, which is the average of the descriptor values for all nanoparticles that were tested over the same element of the experimental condition. This is a kind of ontology, really. So you have an ontology which is you have to collect the data also you can have the same type of nanoparticle, for instance, but one was tested against cytotoxicity and another one was tested against ecotoxicity, or another was tested under 10 hours, another was tested under 20 hours, whatever, which different conditions. So we compute the average for the nanoparticles that were tested against the same element. And this ontology can be expressed in this form, and it's by organizing and grouping the several elements needed for defining specific experimental conditions. And as you can see, we can put, well, everything you have really, and the type of measures of toxicity, different biological targets. If you have tests against algae, fish, cell lines, plants, whatever, you can also put, for instance, the possible shapes of your nanoparticles, spherical, polyhedral, or and the various assay times employed. This can be even larger, and that's why this gives you several much. This expands a lot your data points really, and you can even modify these descriptors, putting if you have some. I don't know if now it's, but there is a famous chemistry database which is ChemBL, you know. And in ChemBL, now I don't, I haven't gone there recently, but in the past they had, if the assay test was, they classified the test that they have, if they were valuable or less reliable and so on. So you can also modify these descriptors by multiplying by a factor which gives you the reliability of the test also. Well, and then what we do also is we kind of also this model is used to classify really, and what we do is a classification model. What we do also, what we have done also in the past was, apart from, you can stop there and using the modified descriptors and then go to the machine learning model immediately. Or you can even go a bit further and do what is called perturbation theory approach. If you know, well, all of you probably know perturbation theory, and it's based on a small perturbation. And what we do is we call these models, which are called the PTML, combine the moving average approach with perturbation theory to handle small deviations of perturbations pertaining to different conditions applied. And so what we do here is the nanoparticles are combined to generate nanoparticles pairs. Notice that this even increase the number of data points really. And of course, in principle, you could use all the possible combinations, which means that you could even use the same nanoparticle, but we don't. And what we do is the nanoparticle pairs are different, really. And in each pair, one of the nanoparticles is used as a reference state, whereas the other is used as the perturbed state or new or final states. And now we are in position to move forward and find possible deviations among the two states by simply calculating the difference. In this case, we did that also to the coatings. So we had the descriptors and the coatings separated, and then we built the models using these delta modified descriptors and delta coating, also the coatings of the nanoparticles. And basically what we then predict is the toxicity based on the conditions used of new nanoparticles as a function of the reference nanoparticle and the descriptors that you have, the difference that you have. So that is the toxicity of a nanoparticle in the new state or perturbed state. Can be predicted if the toxicity of the nanoparticle taken as the reference state is known, as well as these perturbation terms, regarding the elements of the ontology used and the difference among the coatings. And the model then can be established using well-known machine learning techniques. You can even use, well, classification. You can use linear ones, random forest, kind of groups, and couple years later, well, artificial neural networks, whatever. And this, for instance, in this case, we try to improve the ecotoxicity and the cytotoxicity of the nanoparticles of 260 metal oxides and the different experimental conditions, which were, we used 5 types of toxicity measures. So we have CC50, CC50, and so forth. And we had 1 out of 53 biological targets, algae, bacteria, fungi, protozoa, well, some are there, no? And 1 out of 11 possible nanoparticle shapes, and 1 out of 8 possible conditions, and 16 X-ray times, ranging from 0.5 to 360 hours, and 1 out of 16 different coating species. And in this case, we use an artificial neural network classification. We also do the same stuff as we did before. We parameterize we hyperparameterize or we tune the hyperparameters by choosing the number of iron layers and so on, the number of neurons and so on. And we have, this is important to know, we have to have a binary categorical variable, well, a binary or not, but at least this is usually, we use this usually to classification problems. So we have categorical variables, and we have to decide. In this case, we use them for binary categorical variables, and so we had to decide for each of the experimental condition. We had to decide which one was toxic and which one was not toxic, really. And then we had simple chemical descriptors, well, periodical table-based descriptors like the molar value, electronegativity, fluorescibility, and the size of the nanoparticles taken from the experiments. These were quite simple ones, and the coatings were based on well, this software. I don't know if you probably don't know. This is based on graph theory, graph descriptors, really. And so we had 54,000 nanoparticles pairs, which were, this is another thing which I'm not quite keen about. We should not random split into training and test set, really. We should try, this is one of the improvements that we are thinking about in the future, or at least I think we should do in the future, which is trying to use a better way of splitting and into the training and the test set. Because if you are using perturbation theory, and perturbation theory is based on small perturbations, you should not random split into the training and the test set. That's something that we'll do in the future. And we try, in this case, this type of apologies for that artificial neural network, but nevertheless, we had a very good predictive power and correctly classifying 98% in both training and test sets. And then we could also, this was a work done a long time ago, but we could also try to interpret the descriptors that we had. No? But in this case, we kind of use a sensitivity analysis to know which descriptors were what the scripters meant, no? And we end up seeing that increasing the size generally diminish the nanoparticle toxicity. So probably because there is not so much aggregation. Well, then the other types of conclusions that are written there. Well, and we did that also, and we also tried then to kind of virtual screening with some data that was not used. So we applied the model, and this is the percentage of times that this classification perturbation model correctly predict the observed nanoparticle toxicity. So it was quite good, even in some cases not well. Was even so, it's quite good without seeing data. No? And well, I'll stay here. Really, I think. Well, I will say that future work is to, because we have already launched a public available software for the part where you stop without going for the perturbation theory, because we think the perturbation theory, there are things that we can improve using only the moving average approach, which is XAR. Oh, well, we have two, the XAR CO and XAR COX, which is much extended. It's written in Python, so you can change it easily and so on. Because this one is written in Java, and what we should do is also, because coping with by hand with this type of, because we increase a lot the data points. Starting from small data, you increase a lot by exploring the data with the several experimental conditions and then creating the pairs and so on. So in that case, it was 50,000.
Yes.
So we increase a lot the data now, and so this can. What we need also is to, one of these days, to launch a public available software for using the perturbation theory, because we have already, stopping in the moving average approach, we had already launched two softwares. And well, and of course, what we want to do is to generate, do the inverse property prediction, or inverse toxicity prediction in this case. Well, I'll stop here.
Thank you, Professor Natalia, for the very interesting talk. Shall we now move on to the questions? So there are a few questions in the chat. First question is from Tiliban. The question is, I have been working on virtual screening for proteins of interest. Quite often I find that most of the features are redundant to each other among different ligands. Considering the multicollinearity, we have to remove those redundant features, which led to loss of information. It's just a statement. How could you handle this situation? And you mentioned that features were reduced from 440 to 221. Don't you think that it's a losing of data or maybe loss of information?
Well, but we try to. Well, I think if you have, that's my opinion. If you have correlation of the scriptures, you should remove the ones which are highest correlated, really. And what we did was applying the permutation importance to get, and as you could see, in the models won't decrease. There were even in the performance was even better when we decreased the number of descriptors.
Thank you. The next question is, from your experience, what is the optimal number of features should be needed for a machine learning model? Do we need to have more features to have a prominent working model? What is your opinion on it?
Well, I think the first thing you should know when you build a machine learning model is to see if it's not overfitted, really. That's the first question. And then, if it's not overfitted, if those descriptors are not linear, so it means that they are not highly correlated, and if they are not all needed, you can have as much as descriptors. As far as you don't overfit, you know that you are not getting an overfitted model. That is possible. There is no, in principle, there is no limit of the. Well, that's my opinion. I think but the first thing is to check if your model is not overfit.
Thank you. Next question is by Shikhar. What was the reason for choosing the train test split as 60:40? We normally use a split of 80:20. I would like to know the reasons that contributed to that decision.
The decision is that we do a kind of test for the best train load for the models. Although we do that, we could have done that also after we do that before, using the models with the hyperparameters they have, the activation function, whatever they have, and we test the best train load, and then using that the best train load, we change the percentage of the training the test, and then the next step is going for the hyperparameter there. But we could also check again test that to see if after planning the hyperparameters I think, in my opinion, also is that you should not go for a specific number, 80-20 or 75-25 or whatever. You should test which is the best one. When it doesn't start to degrade or start when it goes down, and then when it's already, as you could see on those figures, it saturates, then you stop there. I believe it's better to also to plan the training test.
Yeah.
I think.
Yeah, so could we, let's say, standardize a golden number or a golden speed split, if you would like, let's say, get a multiple types of split? Would it be possible to establish a golden split?
That's what I'm a bit against. I think because it depends on the data you have, really, and I think you should try to check which is the best. Well, that's my opinion, really. That you should check which is the best split in your case. So do a check. And you could even do after the planning of the hyperparameters to check if you should even change a bit more or not. No?
Thank you, Anil. I have a follow-up. What is the underlying reason that this ratio is even important? I mean, 80-20 would be better always. I mean, you train for more. How is this? What is the?
Well, as in our case, by increasing a bit more the test set, we had a decrease of the mean percentage error. So we were having
Observation.
It's an observation, yes. Well, but you have to also to check if you increase very much avoid overfitting. This is also the question.
It's basically going back to the first question that you were saying.
So I believe yes, and I believe, but I believe that you should not go for a. There is no gold number, I think. Well, I don't know. That we could ask the computer science. That probably will. Is there a gold number for?
It's completely depend on the data we have, how much data size we have, and what are
Yes,
the features to play.
Yes, I believe that is really the question.
Thank you. Next question is by Sadanandam. Can you please comment on the descriptor generation process you're going to consider for the catalyst design reaction yields and sources accuracy in their generation?
Well, the descriptors, most of the descriptors that we use for the catalyst design were based on the experimental data. I can go to my. Well, I don't know if in my pen I have that information, but these were kinds of solvents used, time of reaction, things like that. Related. These were experimental data, really.
I have one more question.
And we also did some because the problem with the catalyst design is also that most of if you have if you use some experimental conditions and then you do the catalyst reaction, and if you fail, you don't publish it. That's the problem. So we don't have
The negative data, yes.
which is not quite good for developing machine learning models and try to do an inverse design with which is the best catalyst, really.
Yeah, so yeah, this is regarding your ML model to predict the reaction yield. This reaction yield, even experimentally, can be very complicated since it mostly depends on the downstream processing and the accuracy. So most of the time it is compromised. So how would you, validate that along with your model?
Yes, this is an ongoing work, but we even by collecting the data, we even did a kind of test mining to see which of the articles we tried a lot because in some articles they don't say everything.
Yes.
Yeah. They don't say if exactly the conditions that they are using they are performing the reaction, and in some they say if they use whatever, I can't remember exactly and the others know. So we even try to do a kind of test mining to search for the best descriptors, the best experimental descriptors to check that. And in that, and we had, well, I don't have it here. Have it my laptop I have, but we even did those. We even tried to optimize the features we use. Those type of methods I told you before, the hand colors and things like that to get optimize the best features to describe, because it's quite a complicated thing to model, really. Especially because the data is not clear at all. Some don't say if they are using if the nanoparticle that they are using as a catalyst design, or which type of particular conditions they are using. Some say they use, some they don't use. Well, it's quite a difficult task to handle such type of data.
Thank you, Professor Natalia. There's a question by Prasoon. What kind of cross-validation technique is used? If we only take the top 3 descriptors, if we only take the top three descriptors, I think reproduce the ML model, will it perform better? Let me rephrase the question. What kind of cross-validation technique is used? And if we only take three descriptors, whether we will be able to reproduce the ML model and will it perform better? It's very
cross-validation technique and take the top three descriptors and train the model, whether it will perform better or not.
Not quite understand. If you
Take only top three descriptors from validation, cross-validations, and train the model. If the model is trained by using the top three descriptors, whether it will perform better or
don't quite understand. Well, the consolidation is for the tuning of the hyperparameters, really, no? But if you only take the three descriptors, and what's the question? If the
Well, I think what he's trying to say is that, say, at the end of the day, you saw that few descriptors like surface area, electronic and structural, those are the most important descriptors. So if you take only those 3 or 4 or 5 important descriptors and train the model instead of training with 400 descriptors, how the model will perform, whether it's a right way to do it.
those are the most important descriptors, I believe you can well, I believe also in the alkene reasoning, which is the less you complicate the things, the best it's the alkene reason, saying, which is the less you complicate the things, the best it is.
Yeah. Now, most of the time, I'll tell you why he's asking. Chemical engineers or chemists, they know like enthalpy. Enthalpy is a function of some electronic energies, like some van der Waals interactions and some Coulomb interactions, right? These are the only thing, charge and van der Waals. So any chemical engineer, when they take it, they think, okay, I know the descriptors because I know the physics. I don't need to run through all my adjacency matrices, or I don't need to go for bond order matrices. All these things I can forget about it. Even the molecular weight or all these descriptors, what RTK will go and calculate. I just take these 3 because I know the physics. And I just build a model.
There are I believe there are 2 steps in building a model.
Yeah.
One is the choosing the descriptors, really, and the other one is choosing the hyperparameters of your machine learning model. But choosing the descriptors is also important, I believe.
Yes.
So you should start with and then do the optimization and I believe so. No?
Yeah, what I understand from your talk, the first part, you need some more descriptors because otherwise it will be hyper-parameterized, too much fitting. You need a balance, most probably, with the descriptors. It's not that 3 descriptors or 4 descriptors will always give you the error, right? The error, what you are trying to reduce the error, then you need more descriptors because once there is a small change, the error will also go high if you are not using many.
The problem is that if you only, even if those are the physical descriptors, I think that you can end up with a model that gives you a very low score.
Low score, yes, yes.
I think so.
Yes.
I don't know, but I believe there are 2 things. Which one is handling the parameters of the model, which are the descriptors really, and another one is which that doesn't depend on the data, is to handle the hyperparameters of the model. So I think, because otherwise you can even use for that you use the simple equations that you normally use for that for instance the NIST have, for instance, they have enthalpy variations and so on in terms of the temperature. They have a polynomial function of the temperature
Yes.
or whatever. So for that you didn't have to do a machine learning model, I believe. I think so.
Is any other questions?
Yeah, that is it. That was the last question.
Can I have a final question?
No, sure. No, I'm joking. Of course.
So you're planning to model to predict activation energies for catalysts?
Yes, what I believe we are trying to do is not. I don't think it's. I believe it's reaction yields and enthalpy terms, something like that. I can't remember. And what we often do, well, depends because sometimes you have, if you want to predict the properties, and if for instance that was the case that I show you in a completely different case, which was we needed to have a solvent which had the lower viscosity and the greater CO2 capture, and so we have often conflicting objectives, and you need to have we will try to apply a multi-objective optimization for the two properties. And I believe it was the reaction enthalpies and the yields, something like that. And for that, in some cases you want to have when the lowest yield, for instance, the lowest enthalpy or reaction enthalpy, and the highest yield, whatever. And so we will do. The next step will be to apply a multi-objective optimization tool. And regarding that, what we offer, well, normally multi-objective optimizations are, as the computer science can tell you, is normally they are used by performing Pareto control schemes. But in our case, what we usually do, we use the zeribility function approach, which is an old thing invented by De Ringer a long time ago in the 60s or whatever, which is, we find it, well, don't ask me why, but I know why. The Pareto control sometimes can be quite tricky to have to draw the Pareto front. You can fix some parts and some others, but then and it lacks convergence and things like that. Well, although I'm not into I haven't read much about it. I should study more about it, really, because there should be some type of probably recent developments of the Pareto frontal Pareto control.
Thank you. Thank you. With that, I would request Dr. Roy, who is the CEO and co-founder of Prescience in Silico, to give a vote of thanks.
So thank you, Professor Natalia, for coming here and visiting our office and giving a talk. Learned a lot because sometimes what we do is that solve problem without understanding much, and what I have seen from the machine learning model, the physical properties are coming out, and what basically the physics going behind that's also coming out from a very simple model. So that's actually the hope, I would say, for chemical engineers and chemistry people like us, and we can connect mechanism as well as we can train a model and use the model. So thanks a ton, and I really love that your second part of the talk on toxicity is a huge problem in industry. It's a huge problem in tire industry, in chemical industry, cosmetic industry. It's a large set of problems because we all are looking for ecotoxicity, genotoxicity, and all type of toxicity. I'm going to use this model very soon. Once I have got your QSAR COX module, so we'll go and look at it and see that how we can use it for some other class of materials. And thank you for enlightening us and giving us such a nice talk. And from P-Science, we are really thankful to you for coming here and giving a talk. And to the audience, thank you very much for staying with us. Is actually, we have crossed the timeline today around 20 more minutes. We went extra. Thank you for all staying with us, listening to us, and asking very relevant questions. And finally, I would like to thank Anupam and Meghna for arranging the talk and setting the whole the environment of giving a nice talk here at Pre-Science. We are small, working in a co-working space, but it's great that we got this meeting room and getting things done. And as well as I would like to thank Amir and Jivan for helping us in arranging the talk and smoothly executing the talk. Thank you very much. Thank you, Natalia.
Thank you.
And good night to everyone. Thank you so much.